Well, hello everybody. Welcome back to MI212. This is Mark Gastongay, and today we're continuing with our discussion of advanced pharmacokinetic modeling topics. We're going to build on some of the concepts that we discussed last time, particularly parameter identifiability. And we're also going to talk about these more general structures for modeling. The specific example we're going to use to illustrate that today is modeling of parent and metabolite data in a simultaneous PK model. We'll discuss how we propose that sort of model, what sort of strategies we might use, the issue of parameter identifiability as it applies to those simultaneous models for parent and metabolite data. We'll also address this issue of the covariance of residual random effects. This is the first time that we're able to do that in this course at least, with a multivariate endpoint, and so we'll illustrate how to do that as well. And then adding on to that parent metabolite analysis, which was based on plasma concentration data, we'll add urinary collection data and see what that does to the identifiability as well as the way we propose the model and the data set. And then you'll have a practice problem as an assignment. So let's introduce the model that I'm talking about. This is a simple pharmacokinetic system. In fact, if you look at the left-hand side of the page, you'll see that it's a typical one-compartment disposition model with dose entering some depot or gut compartment, an absorption rate constant, and a parent drug in a central compartment. Here I have it parameterized in terms of microconstants, but you could convert these to physiologic parameters such as clearance and volume as well. The new piece here now is that we've added a metabolite compartment, and we have microconstants determining the transformation or back transformation from parent to metabolite, as well as the elimination of the metabolite. This is the general framework that we're going to discuss today, where we have observed in plasma both the parent and metabolite concentrations. And of course we know the dosing history as we typically would. Well, this model has some challenges. Remember, we talked about a priori identifiability and a posteriori identifiability. Well, the first thing we want to know is this model a priori identifiable? Is there a unique mathematical solution for the model parameters? Or at least a finite solution? And if we look at this model, intuitively you see we have elimination from two separate compartments here, and we haven't administered metabolite, and we're depending upon some estimation here of that transformation. This is inherently an unidentifiable model with respect to all of the parameters presented here. Now, there are a few things that we could do to overcome that. But as it stands, that plasma data model is not identifiable unless we eliminate one of these rate constants. So if we had some knowledge that the parent drug was 100% biotransformed to metabolite and there was no other elimination route for the parent, there was no other elimination route for the parent, then we'd have a system where K20 was 0. There's no exit here. And we'd have only a single elimination. If we have observation of parent and metabolite, that would be an identifiable system. But as it stands, we do have elimination of parent drug and elimination of metabolite. And so we've got to do something else to make this model identifiable from an a priori point of view. So some solutions there could be to fix parameters And the two possible routes here are to fix the parameters, either the fraction metabolized or the volume for the metabolite, or to obtain more data at different sampling sites. So we're going to look at both of these solutions and how they could be implemented in the class today. First, we'll talk about fixing parameters, and we'll look at some NMTran code for doing that. One of the most useful ways to parameterize this model is in terms of an assumed fraction metabolized, or the fraction of total clearance that is responsible for conversion of parent to metabolite. Sometimes that's a parameter that we have a good handle on based on prior knowledge. Maybe we know that a particular metabolite accounts for some percentage of the total elimination of the parent. Or we can always just fix that value and make all parameters relative to that. So that's one possibility, is to fix the fraction metabolized in this route and assume that there's no back transformation. Another solution is that since we don't know the amount of metabolite in the system, we could pretend we know it by fixing the volume of the metabolite compartment. And by doing so, that anchors the amount in this compartment to some known value, and that results in an identifiable system. That's a mechanism for identifiability here that, in my mind, makes it a little more difficult to interpret. I'd rather fix the fraction converted, or just estimate everything relative to this fraction, assuming potentially a fraction of 1. So let's look at that first implementation. This is a model where we have combined data from a parent drug and its metabolite. In fact, this is a model that was used in the paper I shared with you beforehand last week on chlorzoxazone metabolism, where we have parent drug chlorzoxazone and its hydroxy metabolite, hydroxychlorzoxazone, both analyzed after dosing as plasma concentrations. So we're going to use ADVAN5 here. This is a general linear model, and it allows us to specify any structure we'd like, as long as all of the transfers are first order linear transfers. If we had nonlinear transfers between the compartments, we'd need to use the differential equation models, and we talked about that last week. So in specifying the model here, we have 3 compartments. They're named gut, CZX, and HCZX. These are just to label your output in the NONMEM output file. The gut compartment is the default for dosing as well. But notice that we have the CMT data item, which will allow us to specify which compartment, and that essentially overrides any of the default statements. All right, let's think about this structure now. So we're going to parameterize, since it's ADVAN5, we do need to model this in terms of microconstants somewhere in the control stream. That's how ADVAN5 creates the connections. But we could back transform those to physiologic parameters. So what we will need then in this model is these microconstants. So we have K12, that's the absorption rate constant. We have K23, that's the transformation, or the rate constant for transformation from parent to metabolite. K20 is the exit rate constant from the central parent compartment. K30 is the exit rate constant from the central metabolite compartment. So we've made all of these connections here. One of the assumptions that's made, you see we don't have a K32 in this model because we're assuming that this is a one-way biotransformation. There's no back transformation from this oxidative metabolism. Or at least we're modeling a net process that is a net transformation from parent to metabolite and not backwards the other way. Okay. Somebody asked a question here just briefly about the INFN routine. This is not required anymore. This is something we used to use with NONMEM 6 when we wanted to capture some of the internal values. It's really irrelevant in this particular model, and you could actually comment it out. Let's look at the structure of the model then. So we have the microconstants set up. By specifying these microconstants, we've created the model structure I just showed you in the slide above. But we're going to now convert that to parameters that are physiologic, such as clearances and volumes. So first, we're going to talk about the total clearance of chlorzoxazone. That's the parent drug. And you might start this exercise by first analyzing the parent data by itself. So imagine this model with compartment 1 and 2 only, and no metabolite data. We'd run that model, which would be an oral dosing model. You could estimate clearance over F for the parent drug, just as you typically would for a one compartment model. That's a place to start. But I'm assuming we've gone that far now, and we're adding metabolite data. So you have a good estimate of total clearance, or total clearance over F, for the parent drug. And that's what this parameter is here, CLC, clearance of chlorzoxazone, which is the parent. What we're going to do is we're going to use a parameter here that we're calling FM, fraction metabolized, and this is the fraction metabolized to the specific route that forms hydroxychlorzoxazone, the peripheral, or I'm sorry, the metabolite compartment. And that's a parameter that we can't estimate from this current data set. So we're going to fix that to a known fraction. And in this case, there was some good, solid prior information about that fraction metabolized. So then we could define the clearance for both the metabolite, or the metabolic route for chlorzoxazone, and other routes. So it's actually cytochrome P450-2E1 that catalyzes the conversion of chlorzoxazone to hydroxychlorzoxazone, and that's just simply going to be the total clearance, CLC, times the fraction metabolized to that route. But we know there are other elimination routes, such as biliary and other potential metabolites, and that will be described by CLCB, or clearance of chlorzoxazone via the biliary route, and that's equal to the total clearance times 1 minus that fraction metabolized. Okay, so that's one way that we can split the metabolism of the parent drug into its two components, or at least into two components that we're proposing under this model. Then in addition to that, we have clearance of the metabolite, so that's clearance of hydroxychlorzoxazone, that's an estimated parameter. We have a volume for compartment 2, which is the parent drug, and a volume for compartment 3, which is the metabolite. Also estimating a lag time here for the oral dosing. And then we're specifying the rate constants in terms of the estimated clearances. So K23 is the estimated clearance via the metabolic route of chlorzoxazone divided by V2. K20 is the other exit, or the clearance biliary divided by V2. And K30 is the clearance of the hydroxy metabolite divided by the metabolite compartment volume. And of course the scales are necessary here, S2 and S3, because we're observing in compartment 2 and 3 two different analytes. So that's the PK block structure for this model. It assumes linear transfers. Let's look at the error block. We're going to specify now two different types of predictions. C2 is going to be the prediction of concentration of parent drug, and C3 is the prediction of plasma concentration of metabolite drug. IPRED is just specified here so we can capture individual predictions. And we're going to use an indicator variable, indicator equals 0, to switch between different predictions. So we have a compartment data item which allows us to flag that. So if compartment equals 3, indicator equals 1. That means indicator 1 is associated with the metabolite observations. Indicator 0, therefore, would be associated with the parent. So the observations in compartment 3, I call that Y3 here, is equal to F. Now F is going to take on the value of compartment 3 when we are on records where CMT is 3. F is going to take on the value of compartment 2 where we're on records where CMT is equal to 2. And we're specifying a prediction model with a combined residual error. Notice that I have 4 different residual error terms here a proportional and additive for the metabolite, and then a proportional and additive for the parent. Y1 then is going to be equal to F in this particular case. The reason that we can use F here is because we have the CMT item. Alternatively, we could have substituted C2 and C3. So Y3 equals C3 times this expression, or Y1 equals C2. It's up to the user to keep that straight. If you use the CMT data item, NMTram will do it for you. If you're not comfortable with that, you can be very explicit and specify the particular concentration you want for each prediction. And then ultimately, the observed data are flagged by this indicator variable in the data set. So you'll get one prediction here if it's metabolite, you'll get the Y3 prediction, and you'll get the Y1 prediction if it's the parent drug. So it just switches back and forth. And our data set is structured such that we have a stacked DV column alternating between parent drug and metabolite. Of course, there's only a single dependent variable column. So those of you who took the class last year, you saw this when we did simultaneous pharmacokinetic pharmacodynamic modeling. We used the same strategy. Now, the only other thing to think about here is that we're going to estimate parameters of the model, but we're going to fix one of them. And here we see that the fraction metabolized to the hydroxychlorzoxazone route, or the fraction of total clearance, is fixed now to a value of 0.65. So we have some prior knowledge somewhere that 65% of total clearance is via the route to the hydroxy metabolite. This is one way to make this model identifiable. The rest of the model then, dollar omega sigma estimation. We'll talk about some subtleties with dollar sigma a little bit later, but for now, assume those are the same as usual. So I'll pause for a minute, see if there are any questions on this implementation of the parent metabolite model. Okay, no more questions there. Well, that's nice, you know, and we had to, and it will work, and it really depends upon your knowledge of that biotransformation fraction. So that's a question right now. Where does your knowledge of that come from? Could it be from a ratio of AUCs? And it could be. You could look at, particularly if you have similar molecular weights. If not, you might have to adjust them to a molar concentration. But you could look at total AUC and then the fraction of which the metabolite might represent. That could be one way. The real way to do this is actually to have a complete mass balance, and so some mass balance study might have been performed to look at the fraction of total drug administered excreted by different routes. And that's where we're going to next here. We're going to be looking at mass balance by collecting an additional sampling source. One more question here is, if Fm is fixed, why don't we just define it as a constant instead of a theta? And of course we could do that in the code. Instead of saying Fm equals theta 3 here, we could just say Fm equals 0.65. But this construction here allows us to estimate Fm at some later point if we were to collect more data. Either way would work for this model. Another thing that you might do is to just give up and say, I don't know what the fraction metabolized is. I know that this model is identifiable, but this is all I have. I don't have anything but plasma data. And we could assume then, let's say we just assume Fm equal to 1, 100%. Now, of course, that's probably not realistic, but what it does then is it makes all of our parameters estimated here relative to that fraction. And so by just assuming a value of 1, then we're really saying that our parameter estimates are, for example, the clearance of the metabolite divided by the fraction metabolized. We don't know what that is. It's just a ratio parameter. So if you recall, another strategy for dealing with a priori identifiability in addition to the one we just used where we simplified the model and fixed a parameter, is to collect more data, either from another source, another route of administration, another sampling pool, etc. And so that's what we're going to do next. We're going to collect data. In this case, it's urinary collection of parent metabolite. And this is a useful opportunity to capture more of the mass balance of the total dose administered. The tricky thing about urinary collection data is that we don't have a continuous concentration time curve. What we have are batches of urine that are collected in intervals, and we'll have some amount of drug that was in that urinary collection interval. It's not reliable to use the concentration because, of course, urine volume is affected by many factors that might influence the concentration of that drug. So urine concentration is not very useful here. What we want to know is what's the total amount of drug or metabolite that was excreted via urinary elimination in a window of time. So that's the measure we're going to use, is the amount excreted. We could model this in NMTran in a simple way if everything was renal clearance of unchanged parent. There's a default output compartment called compartment 0. But since we have more than one mechanism here, we're going to have to define a separate urinary collection compartment so that the model then will allow us to observe plasma concentrations of parent and metabolite, but also accumulate drug in the urine collection compartment. And this particular model assumes that parent drug is not eliminated renally. It's only the more polar hydroxy metabolite that is eliminated renally. So we're only going to be collecting the metabolite data in the urine. The other routes of elimination for the parent would be biliary and then through fecal elimination. So we don't have to worry about parent drug in the urine. What we're going to measure then is metabolite in the urine. And there's a trick we have to play with the data set. I'll get back to that in a minute. But let's look at the model structure so that we're all on the same page. So now we have the same relationship, first order absorption. We have a parent drug, a metabolite drug compartment with conversion. Again, we're going to assume the one-way conversion of parent to metabolite. So K32 is 0 here, or a net conversion of parent to metabolite. And then elimination from the metabolite compartment isn't just going to some output that we don't have a handle on. We know that metabolite is eliminated by the kidneys and will be collected in the urine. So we now have another observation point, compartment 4, which is our urinary collection compartment. So in fact, if we make that assumption that parent drug is eliminated by biotransformation to this particular metabolite, and that other routes are non-renal or not appearing in the urine, this model is now identifiable because we have a mass balance on the metabolite and we can estimate the parent elimination. So this is now an a priori identifiable model. Now, of course, it depends upon the quality and the frequency of our or maybe the completeness of our urinary collection to determine if this is a posteriori identifiable, but at least we know that it's mathematically unique in its solution for parameters. So one of the things we're going to do then is to code up the data set to collect the urine data. Now, we can't model this as just a compartmental observation because it's an accumulation over time. So what we have to do is structure the urinary data as if it's an integrated amount over time. And so the way we'll do that is we'll collect the urinary amount and allow it to build up until that urinary collection period is over. And then we'll make that the dependent variable then is the total amount collected in an interval and compare that to the observed amount. The way we do that in NMTran is where we very closely tie the data set structure to the model here. We, in the data set, will turn on and off a collection compartment. So we use the CMT data item once again, but what we're going to use is on a dummy data record, so event ID equals 2, we're going to allow that compartment to be turned on and off. So for example, if we specify a row where event ID is 2, that means other. There's no dose, there's no observation, we're just doing something else to the system. And we set CMT equal to 4, that in effect turns on compartment 4. Compartment 4 is open and allowed to participate in the mass transfer of the PK system. Well, what we want to do at the end of the urinary collection is to reset that collection amount to 0. And the way that we do that is we specify another data record, again with event ID 2, at the time of the termination of the urinary collection interval, where CMT is equal to -4. And this designation of a negative compartment number simply means to reset that one specific compartment to 0. This is a very handy feature in NMTran for dealing with resetting single compartments. Now remember, we do have in NMTran the ability to reset the entire system. That's event ID 3, or event ID 4, which allows you to reset followed by a dose in the same record. But that's not helpful here because we don't want to reset the whole system. All we want to do is reset that urinary collection compartment. So we're going to use this compartment and a negative compartment statement with a dummy data record to identify when the model is collecting urine, when it has stopped, when it restarts, and so on. So let's look at the data structure. Your usual stuff here, we have a comment column, ID, time, amount, one dependent variable column. Remember, it's a stack dependent variable. We have a CMT item and event ID. CMT represents the compartment. 1 is for dosing. 2 is for parent drug plasma concentrations. 3 is for metabolite plasma concentrations. And 4 is the urinary collection compartment. So here's how we start. We start off with a dose, and that's as you would do in any case. The second record here, which is really on by default, but we're going to be explicit here, where we specify event ID 2, meaning this is other. It's not a dose, not an observation. And we're just going to say that compartment 4 is on. Now, by default, when you specify a compartment, it's on unless you turn it off. But this just allows us to be explicit about that. We're going to start collection at time 0. Then we have a commented record here. This is at time 0. That's a pre-dose sample of 0, and that's just commented out. There's no need to model that. We follow that by a time series of plasma and metabolite concentration observations in plasma. And you see compartment 2, 3, 2, 3 alternating here. These are matched pairs. Each one of these observations you could conceive of as a multivariate observation. So at any time point, you have the pair of parent metabolite data. Parent metabolite at 0.5, 1, 2, 4, 6, 8, and so on. That's all fine. Well, there's another data record here observed at time 8 in compartment 4. And time 8 in compartment 4, well, it just so happens that this urinary collection interval was for 8 hours. And we'll know that from the data set or from the protocol. And so from time 0 to time 8, where we started compartment 4, up to time 8, there was an observation of this amount here, 170,000 units, was observed in the urinary collection. This is real observed data. This is the amount of drug, or in this case, the amount of metabolite that was collected in urine. We're going to identify that as being associated with compartment 4 because that's the urinary collection compartment for the metabolite. And that's great. But you know what else? We also have another urinary collection period that goes from 8 hours all the way to 24 hours. So what we have to do is to wash out that amount, because now that urine's been collected, we're going to now start collecting again. So then the next record here, which is happening at the same time, but it has to be ordered in this way, is going to be the event ID 2. This event ID 2 signifies an other record. And what are we doing there? We're setting it to -4. There's no dependent variable. There's no observation. We're just turning off the compartment. Okay, so the ordering here is very important. You make the observation at time 8 hours. You empty the urine compartment with the next record. And then you're going to start collecting again. And so we turn on the compartment and the next record. All of these things are happening at that 8-hour time point. It's just that we're making them in the right order. Observation, wash out the compartment, turn on the compartment. And now we're going to collect urine for another 16 hours. And at 24 hours, we have a urinary collection amount. And this is the rest of the drug that was observed or collected in the urine from 8 hours out to 24 hours. And that's what's observed here as the urinary amount collected over that interval. We're going to identify that with compartment 4 again, because that's specifying the urinary collection compartment. And then the last record for this individual, we're just going to turn off that compartment, reset it, just in case we wanted to collect more. But that just so happens that this is a 24-hour study, and we're done here with that individual. So that last record is not essential. That just carries you forward to the future records if you wanted to continue to collect urine. For the second individual, we'd set it up the same way. So the key things here are, number one, making sure the compartment is on, tracking the observations, making that observation of the urinary collection interval at the end of the interval. So the time of the urinary amount is always the time at the end of the collection interval. You make the observation, you wash out the compartment, you reset the compartment, you return on that compartment, okay, and now you start collecting again. At the end of the next collection interval, which was 24 hours post-dose, you make the observation, and so on. So this is how you can use that compartment item. It's a really handy way to turn on and off compartments. Okay, I'm going to take a minute or two to answer some questions. So one question is, what if we have multiple metabolites? How do we deal with that? And you'd have to make a similar set of assumptions that also increases the complexity of the model, and it's just as unidentifiable. But for the single metabolite here, we assumed that we knew the biotransformation in the first case when we're just dealing with plasma data. And we'd have to assume that we know the relative fractions for multiple metabolites if we had those observed. Or we need to collect the mass balance, such as collecting the urinary output of those metabolites, and each one of them we'd have urinary collection compartments for. So it just increases the complexity, but we would deal with it in the same way. Can identifiability cause instability of the model? How about eta identifiability? Can eta be fixed to avoid unidentifiability? Well, yeah, those are different questions. There certainly is identifiability problems both at the population level and the individual level. And you'll notice here that I'm not allowing for an inter-individual random effect on the fraction metabolized. Let me get my cursor back. FM here is fixed to a population level value of 0.65. If we had allowed an inter-individual random effect to be estimated, now all of a sudden you've fixed the population level, but you've made the individual level unidentifiable. So you've got to fix this both at the population and individual level. What's the method used to identify the a priori identifiability? I assume you're asking. There's different methods here. Most of them are gradient based or sensitivity analysis based. And as the models get more complex, it's difficult to intuit where the identifiability problem is. So you using some of the software tools like DAISY that I presented before would be a useful way to do that. Of course, you can also get a hint as to some sort of identifiability problem, whether it's a priori or a posteriori, based on using different sets of initial estimates and looking at goodness of fit and the resulting parameter estimates. But that doesn't necessarily discern between a priori and a posteriori identifiability. So you use one of the software tools that I mentioned last week. But some of these are almost obvious when you look at the model. So this parent-metabolite model, we know for sure that it's not a priori identifiable, because you know that there's an infinite number of combinations here that could allow us to describe this. Right, you could ramp up transformation here and slow down the K30. It's just not. Whenever you have this elimination from two compartments simultaneously, and we don't have collection in either one of them, there's an infinite number of combinations. That's almost one that you could see, obviously. But if it becomes more complicated than using some of these software tools, which look at sensitivity to identifiability, would be a useful thing to do. So the question is, all compartments are open by default. Is there any compartment closed by default? Yeah, every compartment is on by default. As long as you specify it. You could specify in the dollar model statement that default off, but by convention, all compartments are on. The one thing that I've done here is to just be specific about turning it on, just in case we want to add more data. Maybe there's some data occurring before the records observed here, and we might want to make sure that compartment's on. So I was just being explicit here. But this compartment 4, where we're turning on the compartment event ID 2, compartment equal 4, that's not absolutely necessary. Okay. So that's the data structure. This is the model. So we have an additional parameter to estimate here. Well, I'm sorry, we don't have an additional parameter to estimate. We have the same number of parameters. We have an additional sampling compartment. And here's the NMTran code for this model. So everything else is the same as before, except now we have urine collection data in the dependent variable column. An additional compartment as well. Again, remember, you could ignore this INF and, in fact, comment it out. This is really only relevant for some of the work we were doing in NONMEM 6. The model specification has now 4 compartments. We have the gut depot, the chlorzoxazone plasma, hydroxychlorzoxazone plasma, and then the urinary collection for hydroxychlorzoxazone. So the model structure is going to be similar, but now we are going to actually estimate all of the parameters of this model. So K12, again, the absorption rate constant, is estimated. We are now going to independently estimate the metabolic clearance of chlorzoxazone and the other route, the biliary. Before, we had fixed those according to the fraction of total clearance. And now total clearance is just the sum of those two. We can estimate the fraction metabolized now as the ratio of the metabolic clearance of chlorzoxazone to the total clearance. We can also estimate the clearance of the metabolite, hydroxychlorzoxazone, the volumes of distribution for each compartment. This is all identifiable now. And that's assuming, all these inter-individual random effects, it's assuming that we have plasma and urine data from every subject. If we don't have urine data from a subject, now the model is not identifiable at that individual level. And it's going to rely heavily on the population mean results to influence that individual parameter. The microconstants are as described before. We have another compartment now, and we're going to fix the scale of the urinary collection compartment of 1. And that's simply because we're expressing the urinary collection amounts as an amount, not a concentration. So if we take the mass transfer that's being calculated by pred-pp here and we divide it by 1, then we're still in mass units or amount units. In dollar error, we specify different prediction types, again, those are going to be specified by the compartment data item. Now we have 3 different dependent variables, and we'll set up 3 different indicator variables here. They're all 0 by default, but then if compartment is equal to 2, then indicator 2 is 1. If compartment is equal to 3, then we turn on indicator 3. And if compartment is equal to 4, we turn on indicator 4. So at any one time, for any one record, only one of these indicator variables is equal to 1. All the others are 0. This allows us to switch between different predictions for the different compartments. We have 3 different residual variance models, each one of them having their own estimated variance terms here. Both the proportional and the additive components are unique for each analyte. And this makes sense from a bioanalytical point of view, in that we are using different analytical methods for the plasma concentration of parent versus the plasma concentration of metabolite versus the urinary amount determination. And so we're allowing for the measurement performance there to be different across those methods. In addition, there might be different levels of process noise. For example, the urinary collection interval, might be recorded incorrectly, or you might say it's an 8-hour interval, but maybe that wasn't the case. And of course, there's always the issue of residual urine in the bladder, which is not part of the systemic circulation, but really in this model is lumped into the urinary collection. Now, if the bladder hasn't been emptied completely, then of course there's some residual drug in the bladder there. So there's some error associated with that measure, and allowing for different residual variance models for the different analytes helps us to accommodate that. The final statement here is the observed data is equal to each one of these predictions times their indicator variable. Each one of these is on only once per record. The variable that's turned on is the prediction for the compartment that we're concerned with. So at any one time, only one of these is being used in the prediction. If it's compartment 3, it will be indicator 3 or the metabolite plasma concentration. If it's compartment 4, it'll be the urine collection amount. If it's compartment 2, it will be the plasma parent drug concentration. Now, I didn't specify the rest of the control stream here, but everything else is as you would typically do, except for the residual error, which we'll talk about next. But we don't have to fix the fraction metabolized in this model because we have an a priori identifiable system with this urine collection. Of course, the assumption here is that the way we've written the model is the way that the transfer occurs. K32 is 0, so there's no back transformation, and that all of the metabolite is excreted in the urine. Under those conditions, this is an identifiable model a priori. Okay, let me pause a minute and address questions on that model. Somebody's commenting on the output compartment being off. Yeah, for Advan 2 through 4, so the canned models, the output compartment is off by default. That's correct. It's these general models that the compartments are on automatically. And if you wanted to look in that in more detail, just look up the help file for the Advans. In fact, we could do that right now. Let me switch over to the NMTran help. Let's pick Advan 3. And all of these analytically solved packaged Advans start with the central peripheral compartment's on, but the output compartment off. So that is correct. It's just the general models where everything is already on. The general models, like those you specify with Advance 6, 8, 9, 13, the differential equations, as well as Advance 5 and 7, the general linear models. Okay. All right, next question, let's see. Is Advan 5 more efficient for this model than Advan 6? That's a good question. Advan 5 uses a different method for solving the differential equations. It's something called the matrix exponential method. And it's actually quicker than doing a full numerical integration that we would do in Advan 6, 8, 9, and 12. So yes, it is more efficient. There are two versions of that matrix exponential solution. One is with real eigenvalues, that's Advan 7 versus not Advan 5. The only way to really know which one works better is to try them both and to look at run times and convergence success. But for a system where all the transfers are linear in the pharmacokinetic sense, first order, it's more efficient to use Advan 5 or 7 than it would be to write out the full differentials. And you know, you also don't have to deal with the complications of setting the correct integration interval through the tolerance variable. So it's quicker and a little simpler to implement with Advance 5 and 7. Of course, if we had a nonlinear transfer, then we can't use these, and we have to go to the differential equation models. So for TMDD, we have to use Advance 6. That's right. The TMDD model has a saturable transfer associated there, and you'd want to use the Advance 6. Now, if you use the full TMDD model, let me recall that those are, well, you do have that second order process, so you do need to use Advance 6. Okay, back to the notes. Now, I alluded to the fact that when we're analyzing parent and metabolite data simultaneously, it's essentially a multivariate endpoint when we have these sampled at the same time. A multivariate observation. And that happens commonly in pharmacometrics. For example, if we have observed concentration and effect data, and we have those at matched time points. Plasma, urine, maybe you have other data sources that are observed at the same time. Parent and metabolite data, that's the classic example where we have a single plasma sample that's used to analyze two analytes. It could also happen if you happen to use concentration in some biomarker in that plasma. So one of the concerns then is that maybe there is some correlation in the residual error associated with the two endpoints in a multivariate observation. So think about it this way. We have parent and metabolite data that are obtained in a single plasma sample. What if that plasma sample was recorded incorrectly with respect to sampling time? Maybe it was recorded as an hour later than it actually happened. Well, both that parent and metabolite data are going to be affected in the residual error and potentially in the same direction. And so we could actually account for that by allowing a correlation in the residual error between the parent data and the metabolite data. So this is similar to allowing correlation or covariance between inter-individual random effects, where we might assume that individuals with a large volume distribution might also have a large clearance, and so there's a covariance between the random effects for volume and clearance. Well, now we're thinking of that sort of covariance at a different level, where we have a multivariate observation and there's potential covariance in the observations in the residual random effects for those two observations. This really only applies when the multivariate observation is made and both observations are made at the same time. So let's look at how we would model that. Now we have a reason to model the covariance in the residual error. Remember, the sigma matrix is a covariance matrix for the residual error, and usually we're just modeling the diagonal elements here. Recall that this is a symmetric matrix, so the upper right triangle is the same as the lower left. We usually ignore the upper right. And so the diagonal is the variance terms, and oftentimes when we write out the sigma specification in NMTran, we just specify the variance terms. We don't specify the off diagonal. Well, in this case where we have the multivariate observation, two dependent variables observed at the same time, we may actually want to model that covariance. And so sigma 2,1 is of interest now. So how do we do that? Just a reminder before I show you how we do that is, if that covariance is difficult to interpret, we can always calculate a correlation coefficient between those two, and that makes it a little easier to interpret because the correlation is specified on a -1 to +1 scale, where the absolute value closer to 1 indicates a higher degree of correlation. But if we want to turn around and simulate from this model appropriately and capture that residual covariance, we probably want to estimate the off-diagonal elements. Well, it's not just as simple as adding that to the initial estimates for the sigma block. We've got to take a further step here in the data set. Let me explain. We have two levels of random effects in a population mixed effects model. Level 1, the L1 data item, is also known as ID. Level 1 is the individual random effect, what differentiates between subjects. Level 2 is the residual random effect. And if we model interoccasion variability, then we'd have 3 levels. But in NMTran, there are some recognized variables called L1 and L2, and L1 is synonymous with ID because ID is the grouping variable for the inter-individual random effect. We know that the ETAs are identified once per ID, and it's because of that ID grouping variable. If you wanted to try it, you could leave ID out of your data set and use L1 instead, and L1 actually means the same thing. What we need now is a grouping variable for the residual random effects that might be correlated, and that's the L2 data item. This is a seldomly used NMTran data item, but this is the data item that we use when we're modeling that covariance. It's not necessary unless we need to tie together those observations or group them together. So this is the grouping variable for potentially correlated residual random effects. If we have a multivariate endpoint with the two observations measured at the same time, then we would use the L2 data item to assign or to identify that those observations are potentially correlated, and that's the grouping variable we'll need. So how do you do that? Well, first, when you read the help files on the L2 data item, they're pretty confusing, and you have to pay attention very carefully to the nomenclature about NMTran data. So what's a data record? A data record is a single row in a data set, remember, and an observation record is one where the dependent variable is present, or MDV is equal to 0. However, when the help file talks about an individual record, that's the L1 record. That happens to be the block of rows, one or more contiguous data rows or data records with the same ID. So an individual data record is a block of data records specific to a specific subject, and they've got to be contiguous. Remember, in NMTran, if you have a batch of observations for an individual at the top of the data set and then insert that same ID later in the data set, they're not linked. They're viewed as two separate individuals, so they've got to be contiguous. It's there. It's within that L1 record, or the block of individual data records, that records are divided into L2 records, where the L2 record is one or more contiguous data records. Again, they've got to be contiguous with the same L2 data item value. So let's look at an example. Excuse me. Here's a data set with the usual columns. We have a multivariate endpoint happening here with observations in compartment 2 and compartment 3. So this could be parent metabolite plasma concentrations. We have a type indicator indicating parent metabolite, and we also have a compartment indicator. Those two are observed at the same time point, 2 hours post-dose. And event ID indicates it's an observation, it's not missing, and so on. Well, the L2 item here is specified so that contiguous observations within the same subject that have the same L2 item could be viewed as observations potentially correlated in the residual random effects. And so the way I've coded it here is that we have this L2 item for this first observation is 1, 1. Well, those are the same L2, they're contiguous, and so these two might be correlated. And then we go on with some dosing information and so on. And then the next matched pair, so down here we have an observation in 112 hours and 125 hours for parent metabolite. Those are not at the same time point, and you'll notice if you go all the way to the right here that the L2 is not the same. So they're not going to be viewed as potentially correlated. But when we get down to the next individual at time 2, we do have a matched pair, and those have the same L2 data item. When we get further down at time 63.5, you see a matched pair, and they have the same L2 data item. So the key here is to specify the L2 data item so that it identifies the matched pairs of a multivariate observation, but does not link in other dependent variables that are not occurring at that same time point. Now, another way you could do this is if you had time observations that were identical for parent metabolite, as we have here, is you could use the time column as the L2 column as well, and that would serve the same purpose. It doesn't really matter the magnitude of the number here or even the order. It's just that the contiguous records within an individual have a matching L2 label. It's a little bit difficult to get your head around this, but give it a try, and we could look at the help files for a little more detail too. Let's do that. So when you read this help file, you got to be careful to recall what the different labels are, or the nomenclature for different records. The ID record is, the individual record is the record of all the data for a subject. Whereas the L2 record is that set where you have a multivariate observation. So this is helpful here. By default, level 2 observations are treated as being statistically independent multivariate observations. Okay, so the residual error by default assumes that they're independent across a multivariate observation. Here's another example of how you could code it, where again you see the matched observations at the same time. So time 2.0 here, they're matching the L2 data item. Again, the next group down here is matching the L2 data item. So if you have some difficulties in sorting this out, read the help file, and you'll have a chance to implement this in the practice problem this week. Sorry. Okay, any questions on this data structure for L2? Here's one. Is type necessary here? Well, it depends on how you're using the indicator. You could use the compartment as the indicator because that's also unique. So type is not necessary. How would we use time as the L2? Okay. Well, what you've got to be careful of here is in what you label on $input. So you could copy the time column here, but change the header to L2. So that's one way to do it, because if your observations occur at the same time, then your L2 would be the same, right? So all you got to do is copy time as a second time here, label it L2 in the header, label it L2 in $input, and you also have your original time column in $input. Okay, don't use time equals L2 because that's going to confuse things. Just label it L2. So on page 59, well, there's 2 matched pairs and 1 unmatched pair of parent metabolite records. That's right. That's right. You'll notice that the ones that are matched, so here's a matched pair at time 2, there's a matched pair at time 63, but there's an unmatched pair here. Well, the thing that's different is that the matched pairs have the same L1 item, so 1, 1, right? Down here, 4, 4, those are matched. But the unmatched pair that happens at 112 and 125 hours, those don't have the same L2 data items, so we're fine. We're not going to model the residual correlation in that multivariate observation because it's not really a multivariate observation. It's 2 univariate observations taken at different times. It seems that the L2 items assigned to dose records are not critical. That's absolutely correct. L2 data items only are important on observation records. That's right. The 13-hour gap is enough to reduce correlation, apparently. Yeah, so that's the assumption here. Now, remember, we're talking about correlation in the residual random effect at that particular time point. You could have some autocorrelation with some time lag to it, and that's a more complex residual model. But usually what we would assume is that unless they're happening at the same time, and in this case the rationale here is that they're coming from the same plasma sample, because it's the way that that plasma sample is being processed that can induce the correlation in the residual error. So if it's a different plasma draw at a different time, it's not likely that there's residual correlation there. So somebody's asking a question about the dosing record with an L2 item. It doesn't matter. The L2 data item on dosing records is irrelevant. Can the L2 be the same between subjects? Sure. It doesn't matter. You could use the same numbering sequence. Remember, the L2 is looking at correlation within an individual record or within all the records of a single subject. If we use the same pairing variable for the next subject, it doesn't matter. L2 really is only looking at correlation between multivariate observations within a subject. Okay. Can the last record of ID 1 be signed at L2 equal 3? The last record here, yeah, sure. As long as it's not the same as the prior one, that would be fine. This last matched pair is not a matched pair. And so as long as L2 are different variables here, this could be 23, it could be 150 and 291, it doesn't really matter, as long as they're not the same value. And really we're just talking about the correlation in observations taken from the same sample or the same sampling time. Right. So I think we've got it here. It sounds more complicated than it actually is. All we have to do is make sure that when we have correlated or potentially correlated multivariate observations, that their L2 data label is the same and that they're contiguous. Okay, so what that allows us to do is to specify a model structure, and we can specify the PK model or dollar error however we'd like. We're going to have two types in this structure, but when we get down to the sigma block, for example, here we have a PK-PD model where the prediction is equal to a concentration prediction or an effect prediction depending upon the type variable. Each one of these concentration effects has an additive residual error. Epsilon 1 for concentration predictions and epsilon 2 for effect. Well, in that case, we're going to assume then that this epsilon 1 and epsilon 2 could be potentially correlated at those records. They're identified as a multivariate observation. And the way we model that then is as we would in omega, what we're using sigma now, block 2, because there's two elements in the diagonal. The first term here is the variance of epsilon 1. The last term is the variance of epsilon 2. And then this off-diagonal element is the covariance between epsilon 1 and epsilon 2. And this is facilitated by having the L2 data item in the data set. Now this can get a little trickier when you have a combined error model for parent drug, for example, and for metabolite. So what we're looking here is correlating not the additive and proportional within an analyte, but we're looking at correlating the proportional component of parent drug with the proportional component of the metabolite, and maybe similarly the additive component of parent drug with the additive component of the metabolite. Okay, so in that case, you'd have to order your residual random effects in such a way that you can create that block structure. We're not necessarily assuming that there's a correlation between the additive and the proportional component within the same analyte. That's not the kind of correlation we're looking for here. We're looking at L2 correlation across the multivariate observation. Okay, a few more questions. Oh, this error, somebody's asking about this particular model. This is just a generic model. Theta n, n just represents some number. It's not verbatim code here. This is just representing some linear relationship where concentration and effect. This is actually the error block of a simultaneous PK-PD model where slope is an estimated parameter, and so effect is equal to the concentration times slope, whereas concentration is just equal to F. That's not really important to the discussion here. Yeah, it was just all I was trying to do in this error block was to illustrate that we have a multivariate endpoint and to show you how the two residual random effects might be correlated. Okay. More questions? Yeah, so again, just to be clear, the slope piece in here, this is a remnant from another model. Probably I shouldn't have used it here when we were talking about parent and metabolite models. This is actually the way we would code a pharmacodynamic model or a simultaneous PK-PD model. Whatever you use for the prediction. So let's go back up here to the parent metabolite code. Whatever we use for the predictions here, let's go to the simpler one, which is just plasma data. In dollar error, we have C2 and C3, or in other words, a prediction at for the parent drug, which is compartment 2, and the metabolite, which is compartment 3. Both of these prediction models have their own residual random effects. What we would be correlating here is epsilon 3 with epsilon 1, and then epsilon 4 with epsilon 2. What we're saying is that across this multivariate observation, we would allow for the different components of the residual error to have some correlation. we're not allowing for correlation, and it doesn't really make much sense to allow for correlation between epsilon 3 and 4. That's the proportional and additive within the same observation. What we're looking at is correlation between the multivariate endpoint residual random effects. Okay. That's the L2 data item. This can be used anytime we have those sorts of paired multivariate observations. It allows that correlation to be maintained. Hasn't been used extensively in our field. In fact, I think most folks just ignore it, maybe because they don't know about it or they don't bother with the complexity. But the impact could be important, particularly if you're going to turn around and use the model for simulation. So somebody's asking, how do we allow that correlation to happen without one or the other? So let me give you an example. I'll just pull up a text editor here. So let's say we had a model like this. Let me increase the font. So this is your concentration prediction. So let's say Y2 equals concentration, and that's coming from someplace else. Or to be specific, I'll just say C2 times 1 plus some residual error, right, plus error 2. And then your observation for compartment 3 would be equal to C3 times error 1 plus error 3 plus error 4. So you have this combined error model for both parent and metabolite. Okay, and then your overall prediction is going to equal to C2 times whatever indicator variable we've got plus C3 times 1 minus that indicator. Okay. So down here in $sigma, we want to create a block for correlation. Now the way that I've written the model now, it makes it difficult to correlate 1 and 3 and 2 and 4 without the other correlations. So what I'm going to have to do is renumber this. So let's do it this way. So that 1 and 2 are their proportional components for parent metabolite respectively, and 3 and 4 are the additive components for parent metabolite. So what we would do is model like this: sigma block 2, not 22, and you put your estimates for the proportional. Maybe you assume it's a 30%. So that's a proportional piece. And then the additive piece, we need another sigma block statement. Where we'd write, you know, something on a different scale. This is the additive, maybe something like this. So that we have now 4 residual random effect variances on the diagonal. These are the 2 proportional pieces. These are the 2 additive, with the covariance now allowing the correlation between those 2. So the way that you have to do this is to make sure that you number things in order. So 1, 2 would be specified in this first block, 3, 4 would be specified in this next block. That's the trick. In fact, I'll take this and I'll insert it into the note set for you, and I'll post a new version. Okay. Question, is it correct to think that correlation is more appropriate for immediate effect, not for delayed effect, such as indirect PD models, PK-PD models? It probably is the case if you have an indirect response relationship. However, if there's process noise affecting both of those observations, there could be some there could be some correlation there. If you're not sure, it doesn't hurt to model it, and you'll see that correlation might be close to 0, and maybe you could ignore it. But if you're unclear as to whether or not you should do it, why not try it? Okay, how do we know which error should be correlated to one another? Well, again, this is a modeling decision, or based on some knowledge. So what we're saying is that the error associated with one analyte is correlated with the error to another. What I'm thinking is a reasonable thing to do is to say that the additive component of the errors, or the additive source, might be correlated, and the additive source might reflect things like process noise, errors in recording of sampling times, and so on. And the proportional error might be assay performance. So let's say somebody diluted that sample incorrectly. That assay part of the error might also be affected. So I think it's reasonable to correlate error 1 and error 2 here. We don't want to correlate error 1 and error 3, or error 2 and error 4, because there's no rationale for doing that. That's within a particular analyte and two different causes of the error. We'd assume that those are independent. But things that might be involved in the same process, we would want to correlate. Okay, one more question. Let's see. Will this cause over-parameterization, causing instability? No, it shouldn't. Remember, what we're doing by default is modeling a matrix like this, but we're just fixing the off-diagonal to 0. And so this actually gives us a little more flexibility. If you have the data there, you should be able to estimate it. It might run into some trouble if you have very few samples, very few multivariate samples within a subject. Let's say you just have one pair within a subject. Then it might be difficult to estimate this correlation, and you could have some convergence difficulties. Okay, so you're, if we're done with the questions there, I'll go on to the problem. I'm going to give you data sets now. Plasma drug concentration for parent and metabolite, plus some urinary data. And I'll give you these. I haven't posted them yet, but I will post them as soon as we're done with class. And they'll be in separate pieces. You'll need to put them together into an NM-Tran data set. Then I want you to construct a simultaneous population PK model for all of these analytes and estimate the parameters. In addition to that, I want you to look at incorporating an L2 data item for matched pairs of parent metabolite plasma concentration data. You don't need the L2 item on the urinary collection, but on the plasma concentration pairs, I'd like you to incorporate the L2 and estimate the parameters for that. So I'm going to give you the data set. The lecture notes have a starting point for the control stream. Remember, you're going to be using the second example we talked about, this control stream here. And in fact, it's the same data set that I used for this hydroxychlorzoxazone and chlorzoxazone data set. So your model structure is pretty much laid out for you here. You just need to construct the data set appropriately, run the model, and see what happens. We'll review that on Friday. There's no reading assignment for this week. I'm giving you a short week on homework here. And the next topic is a bit of a review where we're going to talk about simultaneous PK/PD models and indirect response pharmacodynamic models as a setup for the next series of lectures. Those of you that took the MI210 course, this will be a little bit of a repeat, but those of you who have not, I wanted to make sure that we have this review session complete. So no reading assignment for this week. We're going to have a review of some simultaneous PK/PD modeling next week, and then we get into some more complex PK/PD models following that. So I owe you a couple things. I need to post the example data sets, and I'm also going to incorporate this example of coding the error block for a multivariate correlated endpoint where you have a combination residual error model. We'll finish up with just a final question or two, if there are any. No more questions? Okay, great. So thanks for your attention. Again, I'm sorry about the change in schedule this week, but hopefully if you missed the lecture, you'll be listening to the recording, and we'll pick it up again on Friday with the problems for parent metabolite modeling. Thanks for your attention, and look forward to speaking with you on Friday.